Hello everybody. This is your first video on the chi-squared unit. That's unit 9. I just want to remind you that this is an extra thing, right? Because of this crazy quarantine business, it's not going to be on the AP test this year, but I still think it's a really useful thing and a useful skill for you to know and to know how to do, especially if you want to do anything science or math related later in your life, or even if you want to do something in the social sciences like psychology or anything like that. I've seen it used in like business relations and all this kind of stuff, right? It's just another way to analyze data. So I think it's an important thing to at least have a foundation for. So that's what I'm going to show you. This video is just about the basics, the chi-squared basics. And then there's 3 different types of chi-squared tests. So I'll make a video for you on each one. The cool thing about chi-squared tests is that most of the time, the calculator is going to do most of the work for you, which is pretty great. So stay tuned for those individual test videos. This is just an overview. I want to give you a general idea of what chi-squared is. Okay, so up to this point, we've been dealing with really comparing like 2 different things, right? Like one sample with a population, or we would compare like a population proportion to a sample proportion. But a lot of the time, things are not going to fit into just 2 categories, right? Like either it is or it isn't. So a perfect example is like if you think about a bag of marbles, or like in the case here, I have M&Ms on the screen. Those obviously an M&M can fit into many categories, right? There's 6 different colors. So if we wanted to show maybe that one of the colors showed up more often in like a bag of M&Ms, for example, we would have to do a one sample comparative test. Like we'd have to take that one sample and compare it to all of the other colors, right? Compare that color to all of the other colors. So you'd end up having to run like 5 different tests, which is a lot, right? It's a complete pain, right? You don't want to have to do that. So that's what chi-squared is for. It allows us to compare lots of categories at once and figure out if one category is different than the others, or if maybe one category is different than what was advertised, right? Like maybe the company tells you there's a certain distribution of colors, but we want to see if maybe it's less or more or different than what the company says, right? So that's what this is used for. So this is something that I actually like. If you have the ability to do this at home, you can, like this little experiment with the M&Ms. I'm going to be circling back to it a couple of times just to give you an example and show you a couple of equations and stuff. I just realized that I still have my blanket on. Sorry. It's still spring break for me, and it's cold in my house. So I'm over here wrapped up in my like snow blanket. So, all right. So let's talk about chi-squared a little bit here. Okay. So here's the basics of chi-squared, and I've got to scroll down just a smidge. Okay. So if you see on the left side of your screen, right here, this is a chi-squared distribution. So very similar to a T distribution, that there's a different curve for every degree of freedom. It's the same thing with a chi-squared test. So, or the chi-squared distribution. So as the degrees of freedom increases, you can see here, it looks more like the curves that we're used to, like the normal curves, right? So in general, the chi-squared distribution is skewed to the right, and it only has positive values, okay? And the reason for that is because we're always dealing with proportions, with chi-squared. So it's always going to start at 0. And it's because it's essentially a distribution of individual chi-squared values, and chi-squared values are always going to be positive. And then you add them together, like it has lots of different components. And I'll show you what I mean in a second. It'll make sense when you see the formula for it. Okay. But in general, it's going to be skewed to the right, only has positive values. As the degrees of freedom increases, as you can see down here in this picture on the left, that as the degrees of freedom increases, it looks more like a normal curve that you're used to seeing, right? Like the degrees of freedom of 1 is really, really skewed to the right, right? Because you see the tail here, it's really skewed to the right. Degrees of freedom of 4 is less skewed to the right, and degrees of freedom of 8 is even less skewed, right? So as you increase and increase and increase degrees of freedom, eventually it'll look like a regular normal curve, okay? Then there are 3 different types of tests for chi-squared, and they are goodness of fit. It's normally abbreviated GOF, because we don't want to have to write out goodness of fit, homogeneity and independence. Okay. For the most part, homogeneity and independence are almost exactly the same. The only difference between them is how you write the hypotheses. Okay. In general, homogeneity and independence are used for two-way tables where each variable has more than one category, right? So say, for example, you were looking at 3 different restaurant locations and then maybe 3 different like menu items, right? So there's like 3 categories across the top of the two-way table and 3 categories along the side, right? So those would be homogeneity or independence. Goodness of fit would be more like the M&M problem, which I have up here, where you only have one category, right? The category is color, right? And like you're just looking at M&Ms, like the number of M&Ms in each category, essentially. Okay. And then very similar to how we did t-tests, degrees of freedom is still something minus 1. In general, our general formula for it, it's the number of categories minus 1. So, for example, in this one up here for the M&Ms, there's 6 different colors of M&Ms, right? So the degrees of freedom would be 5. 6 minus 1 is 5. Okay. All right. And then in general, when we're talking about like how you actually calculate it, chi-squared has its own special formula that we use to calculate it. So if you think back to when we did like z-tests and t-tests, you had to calculate a z value and a t value, right? Where you did like statistic minus parameter, something minus something over something else, right? So you would see something like this. Remember, so like z equals x bar minus mu divided by standard deviation. Remember that? Okay. So, and then t had a similar thing. Actually, I completely messed that up. Sorry. This should have been a t right here, not a z. With z, you would have used proportions. You would have used proportions. So let me change that because that should be a t, not a z. We don't want to get confused because this stuff actually is on the AP test this year, right? So chi-squared has a formula that's similar to this, right? So when we're doing chi-squared tests, the goal is to get a chi-squared value. And the symbol for chi-squared looks like this. It's like a fancy X squared, like it actually is something squared, okay? And there's a formula for that, which I'm going to show you in a second. it's similar to this formula with a couple of little changes, because you have to do some squaring and you divide by a different thing. And again, I'll show you in a second. But essentially what you're doing when you're running chi-squared tests is you're trying to get this chi-squared value, and that's like your t value or your z value. And then you use either a calculator you remember the PDF and the CDF, right? You use either a calculator or you use or what's called a chi-squared table. And I'll show you briefly how a chi-squared table works. But you really won't use it very much. The calculator is a much more accurate way to do chi-squared. Just like remember when we did t-tests, I told you the only time you're going to use the t-table is to figure out your critical value when you're doing confidence intervals. For the actual test, you want to use the calculator because it's much more accurate. Similar thing here. Okay. So, one other thing I want to tell you about these three types of tests here, which I touched on before, that homogeneity and independence are very, very similar because you're using with two-way tables, two categorical variables, while goodness of fit tests only have one categorical variable. For homogeneity, you know that you're dealing with a homogeneity test if you have individual samples that are taken from a population, or you're dealing with like an experiment where subjects are randomly assigned to treatment groups, which is what I'm looking at right here. And then independence is like when you take the sample and then you run the whole test and you gather all the data and do your whole experiment, and then you classify the subjects later, right? So there's no like random assignment going on essentially. Okay, give me a second to pause because I do want to show you the formula for how we calculate the chi-squared value, this value right here, but I have to move some stuff around on my screen. So hold on, I'll be right back. Okay, so let's talk about briefly what the actual chi-squared statistic is. Okay, so like I told you before, the chi-squared statistic has lots of different components because it deals with things in either a one-way table or a two-way table. You have lots of categories and lots of blank spaces. So each category or each possible selection in the category will contribute to the chi-squared value. Okay. And depending on how different the expected value is from what actually happened, the different categories will contribute in different amounts to the chi-squared statistic. Okay, so the formula for the chi-squared statistic is here on the left of your screen, in that green box, but I am going to write it out for you so that you can kind of see the way that it's written. And I'm obviously not going to write all of the words that are there because I'm going to run out of space. Okay, but chi-squared, the way that you calculate it is it's the sum of the observed values minus expected values squared divided by the expected values. Okay, so let's break this down a little bit. So the difference, first thing you have to understand with these is the difference between the observed value and the expected value. So observed value is like what actually happens when you gather the data or when you run the experiment. Like how many blue M&Ms were there, right? So say I have like 100 M&Ms in front of me and 20 of them are blue, right? I count them out and 20 of them are blue. That's O. That's my observed value. That's what actually happened when I ran the experiment. The expected value comes from the distribution of proportions that's given to you at the beginning of the problem. So if we go back up to the M&M problem, it said that the company says that they make 24% of their M&Ms are blue. Okay, so if I have 100 M&Ms, then that means I would expect there to be 0.24 times 100, so 24 blue M&Ms, right? So that's what the expected value is, which you should be familiar with because we talked about expected value when we did probability, right? So it's the number in your sample times the proportion that you think is supposed to be in that category, NP. Right? I'm hoping that looks a little bit familiar, right? You've also seen it when we did sampling distributions. Remember back in Unit 6 and Unit 7, you had to check this goes with one of your conditions, right? This guy right here goes with one of your conditions. Remember NP and N1 minus P, right? So NP was like your number of successes, like your how many you would expect to actually be there. Okay, so that's your expected value. Okay, the reason that we have to square it is because your chi-squared value cannot be negative. So very similar to the way that we calculate standard deviation, we have to make sure that this part where the subtraction happens is positive. And so the way that we do that is we square it, right? That's the only way to guarantee that this number up here, the O minus E, is positive, right? Like in the example that I just gave, O was 20 and E was 24. So this would be -4 up here, okay? And then we'd square it and we'd get 16. Okay, and then E, again, is still the expected value. So if I put 24 here, I would put 24 here. With chi-squared, you have to do that for every single category, right? So up here, when, like if we were in class, I would have you actually do this with M&Ms, right? You would do the observed number minus the expected value, square it, divide it by the expected value again to get the brown M&M component of the chi-squared statistic. You'd have to do it again for yellow, for red, for orange, for green, and for blue. And then at the end, you would be able to add all of those up. That's the sum part, right? Add all of them up and you get the chi-squared statistic, right? So again, that's like your Z value or your T value. It's the test statistic part of phantoms, okay? And then I'm going to touch more on this obviously in the next video, but see these conditions, they come up again, okay? And then with reading the actual table, which I'm going to turn my fancy pointer on here. So when you're actually reading the table for chi-squared, it's very similar to the way you read the t-table. You would look for the degrees of freedom right here on the left side, and then you would read across to try to find the two values that were closest to the chi-squared value that you calculated using this formula up here, the statistic. And then that would give you, see up at the top, a range for your p-value. So again, not something that's super, super useful because it doesn't give you an exact value. It only gives you a range. So the easiest thing to do actually is to use a calculator. Like you'll see when we actually go through and run these tests that the calculator is a much easier way to deal with chi-squared. It runs most of the test for you, gives you all of your information. It will calculate this statistic. It will give you each component, right? Like the calculator will do all of the things, which is great. Okay. So those are just the basics for chi-squared. Okay. Like I said, there's 3 different types of chi-squared tests: goodness of fit, homogeneity, and independence. I'm going to make you a video on each one so that you see how the tests are run.